So this breakout session will deal with the topic, how can we improve energy efficiency at wastewater treatment plants? How can we secure the plant's own power supply in the long term? And additionally, how can we integrate the plants in the energy system? And I'm looking forward to the first presentation. This will be given by Tosca Sech, and she will present a project of the Schwarzach Group for an energy intelligent wastewater treatment plant. Tosca Sech, the floor is yours.
Hello, everybody. I hope you can hear me now and you can see my shared screen. Welcome to my presentation about energy intelligent municipal wastewater treatment plant. It's a full-scale demonstration plant in a project in Bavaria. As Ms. Rechenberg already said, it's the aim of this project was to demonstrate that we can close the loop between two sectors. It's the water and the energy sector. The first thing I want to talk about is what is an energy intelligent wastewater treatment plant. In academics it's already discussed a few years, and some or most of the parts are already demonstrated on bigger scale wastewater treatment plants. But what we wanted to show is that also smaller wastewater treatment plants can manage and handle energy intelligent wastewater treatment. So what are the key factors of this concept? We have focused on the production side of the energy, and we were thinking about what energy do we need, or what are the potential energy sources we have. So we found that we can supply energy from hydroelectric power, from photovoltaics, from CHP unit, and we can enlarge the storage capacity so that we can combine all those producers and also the consumers by a smart grid. So we enlarged the wastewater treatment plant by a bigger biogas tank, storage battery we usually don't have on wastewater treatment plants, and also a bigger thermic storage. All those components together have to be managed by a smart grid and supported by a software that is integrating all parts of this. The opportunity was, or we wanted to take, is also to integrate the energy sector and the water sector. That means we wanted to supply our surplus energy to the local grid, and we want to operate the wastewater treatment plant in a so-called grid-friendly mode. Next slide. I hope that it's not unmuted. Can you still hear me?
Yes.
Okay,
hear you, and
then
we can see the slide.
Perfect, then yes. So the wastewater treatment plant, the demonstration site is located in Schwarzenbrock. The design of this plant is 35,000 person equivalents. That means is size wastewater treatment plant size 4+. It's not a very big wastewater treatment plant, but still size 4. That means a second biggest size class of wastewater treatment plants in Germany. The design parameters are that the future limits of these wastewater treatment plants are increased. That means we have to discharge wastewater up to 5 milligram per liter ammonia and 1 milligram per liter phosphorus. And also we increased slightly the capacity of the plant from 168 liters per second total inflow to 220 liters per second. Important was to think about energy already from the start, also in the planning process. So the first planning decision was to create a wastewater treatment plant with a step feed biological nitrogen removal. This can be seen on the plan on the left-hand side in the south of the wastewater treatment plant. And also what we planned from the start is a process water treatment, and in this case a deammonification, which means very low energy consumption. So the idea was to focus on energy on this wastewater treatment plant and to create the first energy intelligent wastewater treatment plant in Germany without co-fermentation and in size class 4. The project Energy Intelligent Wastewater Treatment Plant Schwarzenbrock was funded by the German Federal Ministry for the Environment and many more, with an amount of almost 4 million euro. The total project costs are about 25 million euro. As I already said, we created a smart grid to combine all electrical and heat producers with the consumers. The challenges was the spatial temporal harmonization of decentralized energy production and energy consumption. And we hope that the project contributes to a cross-sectoral energy efficiency, that the plant CO2 emissions are to be zero in the end, as due to the fact that we only consume renewable energy, and we want to totally avoid the expansion of national power grid and local distribution networks by serving as a net-friendly wastewater treatment plant. In the planning process, we started with simulation of a summer day and a winter day in order to show that all those storages we want to install are really necessary, and that the sizes of the storages are also sufficient. On the left-hand side, you see the simulation of a summer day without storage capacity, and on the right-hand side with storage capacity. As you can see, we result in a very low use of the grid. Total or the calculated storages we needed are for the intelligent wastewater treatment plant are listed on the right side of this table, and the conventional wastewater treatment would have less storage. As I mentioned before, what is essential for the management of all those energy stakeholders is energy management software. The software adapted in this wastewater treatment plant was adapted in order to have a completely overview of over all those components. The main factors are the collection and visualization of all energy data. We have a real-time observation and an analysis. We have a self-adapted continuous forecast of energy demand and energy consumption and production on 3 different time scales. It's from a few hours to 5 days. We have a real-time optimization and control of energy management system, and we have a foresight management, including weather forecast and rain forecast, by using flexible producers, storage, and even new flexible consumers. In the next slide, you can see a picture of the construction site in September 2023. So the wastewater treatment plant is already in operation. Also the sludge treatment. At the moment, we are about to test the operation of the energy management system. It started in October. In December, we will start with the operation of the hydropower plant, so that we can say at the moment, currently we are operating in optimization mode. Next year, we plan the start of the monitoring program to verify the project goals over a period of 1 year. And in June, the official dedication of the wastewater treatment plant is planned. For the results, this is a bit earlier to confirm all the project goals, but what we can already report is that we reduced the energy consumption of the wastewater treatment plant from about 40 kilowatt-stunden per person equivalent and year in the old and the former wastewater treatment plant to about 23 kilowatt-stunden per kilowatt-hours per person equivalent and year of the new wastewater treatment plant. And I'm sure during the optimization mode, we can further reduce this figure. Maybe at last, some ideas. What are the main challenges and of this project, and what are the challenges for further applications? What we think is one major challenge that up to date, there are no legal requirements for energy consumption. We are looking forward to the new European wastewater directive. Maybe those requirements will improve energy management on wastewater treatment plants already. The second, maybe for some plants, the most important factor is costs. We have additional costs for the energy intelligent infrastructure. First of all, we need highly energy efficient units that usually cost more than conventional energy or unit, whatever pumps or whatever you want. Then we have additional units for energy production. We have costs for the storage units. Of course, we have the cost for the energy management system that might be reduced in the future when it becomes a standard product. And we have costs of training and human resources, of course. Another challenge is the collaboration between sectors, water and energy in this case. On a local basis, there might always be some negative reactions towards the idea, because then also the energy consumption is reduced, and the main idea of the energy or the EMU is normally to sell their energy and not to reduce or to sell less energy. So one example is also the feed-in tariffs that have to be changed in order to make it more attractive to wastewater treatment plants to become grid friendly. And last but not least, this is a wastewater treatment plant that is constructed completely new, but the real challenge will be to implement those things on reconstruction sites. Thank you for your attention, and the floor is open to your questions.
Yeah, thank you very much for this really inspiring presentation. And we have a couple of questions. We have a couple of questions dealing with the energy sources. One question is, why do you exclude wind power? Second question is, how do you link your sewage treatment plant to the hydropower plant? And second question to this topic is, how you link an asynchronous energy source with a synchronous with a synchronous management of a sewage power plant.
Okay, I start with the first question. We didn't exclude wind power. It was just that there's not much wind on this site where we built the wastewater treatment plant. As you could see on the picture, we are very close to the next. No, I think it's not shown, but we are quite close to the next houses or to the next buildings of our wastewater treatment plant producers. So this is one thing. And in Bavaria, as you might know, we need a minimum distance to houses of 10 times height of the wind power plant. So this is one thing. The other thing is that we are in the middle of the woods, so there's not much wind in on the bottom.
Hydropower?
Yeah, and a second aspect is that we have enough space for photovoltaics, so we didn't expect to need another energy source, as we already had. And for the hydropower, we expect to have about 6 to 10% of the total energy consumption of the wastewater treatment plant from the hydropower. So it covers already 10% of the total energy demand, which is quite a lot for just a single source. What was the question about the hydropower again?
How it is linked to the wastewater treatment plant.
It is installed right before the effluent pipe. So it's quite close to the wastewater treatment plant. It's not far away. The distance is about 10 meters height, and maybe around 30 meters distance. So it's quite close, and it's completely integrated into the process or the all functions of the wastewater treatment plant. And the second was about the synchronization of the power sources.
Exactly.
it doesn't it doesn't work independently from the grid. That means we are not autonomous or completely autonomous. We can work completely autonomous by the CHP units, so they manage the synchronization. However, we still do take energy from the grid, and also we give energy to the grid. The idea is not to be autonomous completely. Just we want to make sure that we do not take energy from the grid when the sun is shining and all photovoltaic plants are giving energy to the grid. We want to make sure that we take the energy from the grid when it has energy. That's why we are operating the CHP units during the night, and we are taking the photovoltaics energy during the daytime. That's the basic idea of this system.
Okay, thank you very much. A short last question, and then we have to proceed. Becoming climate neutral, how you are dealing with the carbon dioxide emission from biogas or the methane emissions from biogas?
Methane is completely used in this CHP unit, so it's completely destroyed, and we do only we have only CO2 emissions at the site, apart from primary emissions from nitrogen nitrogen dioxide. So that's all.
Okay, thank you very much. Thank you very much again for the presentation, and congratulations to this really inspiring project. And now I want to hand over to Philipp Decker, and Philipp Decker presents a digital model to optimize the energy demand of a sewage treatment plant. Philipp Decker, the floor is yours.
So yeah, as I was saying, so that this presentation here is about how can we incorporate process simulation tools, and well, the fact that we can actually simulate the process itself into the operational aspects of a wastewater treatment site, and how we can use that to optimize, well, in this aspect, the energy efficiency of the site. Where I would like to start off is what Siemens essentially understands under the term digital twin, or the buzzword digital twin, where it starts, where it ends, which tools we can use, and then how we can apply that to the wastewater treatment site. So if we look at the entire plant life cycle, you obviously have your engineering at the beginning, where that is plant design, feed, construction. You have the engineering and the commissioning. So how do we design the process? What do we build? How do we build it? Which technologies are we using? And then later on, the operational aspects. How do we operate it? What is the best operating point? How do we maintain it efficiently? And for all of that, we use, well, we can offer Siemens tools. What I would like to focus on in this presentation is essentially the process aspect of the digital twin, or the process digital twin, which comes into play in the optimization and the operational aspect. And here I would like to, well, not show, but highlight GPROMS as a process environment tool, process environment, CIMIT as a as a simulation tool for the automation system, and the actual automation system, which would be Thematic PCS7 or Thematic PCS Neo, and the gProms digital applications, which allows us essentially to couple the offline model with the DCS on site to enable us to have a real-time optimization. Now, what are the challenges that we face during wastewater treatment? So generally speaking, it is quite complicated to run a wastewater treatment site, because on one hand, you have legal requirements for the effluent, which constrains you quite heavily. You have a variant influent, where that is with respect to load or with respect to amount. And the biological and the chemical networks and reaction networks that do occur during each of the process steps is quite complex on one hand, and it incorporates very slow dynamics. So you'll not immediately see if you're taking a control action if the process is heading into the right direction. What can we do? Well, there are two options, or two solutions really. The first one being an operator training system, or OTS, which essentially links the DCS with the process model, and that enables, well, as the name suggests, to train operators on normal operation, as well as during extreme conditions when there's a heavy rain event, or there's, I don't know, something wrong with the plant, or a line trips, or sensors are failing, whatever it may be. And that sort of allows you to prepare your current operators, but also make that transition from older stuff to newer stuff, well, less painful and more straightforward. The other option is that you can have the model run offline and simulate it offline, which essentially comes into play when you have a very small size plant, where we talk about a couple of thousand, couple of 10,000 of PE. Or you can take the entire thing online, have it directly connected to the DCS, whether as in closed loop or within human in the loop. And that enables you to run effectively sites that are 500,000 PE or bigger in a fully automated way. And yeah, that should give you enough sort of a financial benefit to invest into these technologies. And that, yeah, has the upside that it also helps with climate. What are the tools that I just mentioned? So we have gProms, or gProms is the simulation tool that we build our models in. And gProms is the underlying platform that is used, which houses all the different solvers, all the different functionalities, whether that is steady-state dynamic optimization, simulation, parameter estimation, model validation, etc. On top of that sits the environment that we use to build our models in, where that is through custom equations or through pre-existing library models. And in there, we use the wastewater library, which houses all the units that you would need, whether it's an aerator tank, a settler, digester, etc. And given the background from gProms, where it's heavily focused on the chemical industry, that allows us to also incorporate things like CHP, boilers, engines, treatment sites for upgrading the biomethane or the biogas to biomethane, grid integration into the gas network, advanced CO2 capture, etc. So all that can be incorporated if need be, and whatever the site is sort of allowing and using in terms of technology. gProms itself is the desktop tool, and once you have the model in there and you're happy with the accuracy, you can then embed it online into the digital applications platform, or GDAP short. And GDAP essentially is the interface between the offline model and the DCS, where you relay tags, relay real-time data into the model, and whether it runs fully automatic with certain time triggers, where it runs an optimization every hour or every day or every week. And directly writes into the DCS where it sets new set points for the oxygen controller or for the return sludge or the MLR, or it gets sort of passed on to the operator where the operator then needs to accept the optimized set point. The digital twin itself of the wastewater treatment site, as I mentioned earlier, has essentially two use cases. How are they built up? On the left-hand side, you can see the operator training system. So here we use the GPROMS master model, which is validated and built offline. It is then connected to CIMIT. CIMIT itself is essentially a virtual representation or a simulated version of your control hardware. And that allows you to have all the actuators acting as they should do in the real world, but you have it as a digital representation. And that sort of gets information from the OS of the DCS, where there is no direct feedback, meaning that you can train operators directly on the system where the control hardware is simulated in CIMIT, the process hardware, or not the process hardware, but the process itself is simulated in GPROMS, and it is fed by actual live data or what-if scenarios, depending on whether you want to run those. And there is no feedback loop, essentially. So whatever the operator is doing during the training on the system itself is not getting relayed back into the actual site, meaning that you can train on an offline version of your actual plant. If we look at the real-time optimization aspect, we're using the exact same model as we would during the for the operator training system. That is, as I mentioned, wrapped into GDAP or Digital Applications Platform, and is then connected via an OPC-UA port and the OPC-UA server hosted in the DCS, and gets data, relays it into GPROMS. It runs the simulation, runs the optimization, and sends back optimized set points for your different controllers, depending on whatever aspect you want to optimize. The most normal case is an energy optimization, where it runs the optimization for all the different pumps, for all the different blowers, and it will also keep in mind the effluent quality and the permit levels as a constraint. So you're sure to not run over your permit levels and get fined. Something to note here is that the real-time optimization, or the RTO, is completely vendor agnostic. So it doesn't have to be a Siemens DCS, could be whatever, Rockwell or a SCADA system even, as long as there's a direct connection via OPC-UA possible into the control hardware. That's perfectly fine. How does the digital twin fit next to your real plant? So on the process level, you have your actual site. In the digital process twin, you have the model in GPROMS. If you go to the field level, you have your actuators and sensors of that are represented by the physical hardware in your plant, and they are used or simulated by a CIMIT. The automation level is exactly the same for both, where on Siemens hardware you have your SIMATIC, and on a virtual level you have the CIMIT virtual controller, which has a one-to-one integration into Siemens product, and then you have the HMI level where the operator sits, and a digital twin on top of the HMI, where there's a direct feedback link or feedback loop. You have the digital application platform, which again houses the master model, receives up-to-date and real-time data. There's some data validation already built in, cleansing faulty sensor data, etc., and gives you a whole representation of the current state of the plant. And with that, you can then look at soft sensing. How do we take plant measurements and infer calculated variables based in real time, so you're not lacking information, or you get additional information as an operator. and you don't have to wait for the next lab measurement or the next measuring campaign, etc. And that helps you to sort of monitor the process as well as, well, diagnose any problems. On the other hand, you have the real-time optimization where you're even able to read in the electricity prices if you have a CHP plant, and you look at what might actually be worth now. Should I store my biogas for a later point because electricity is pretty cheap at the moment, or should I use the biogas now in a CHP and save the money I would spend on importing electricity? And if you have all that information, you can then run the optimization and get recommended optimal set points for your control variable. How does that look like in the flash or in the ones and zeros? So what you have here is the gPROMS environment with all the different libraries available to you. Very easy flow sheeting. You just drag and drop the different units, connect them up, specify them. Ideally, that's it. Similarly, as simple as it is, you define your objective function, you set the decision variables. So which variables do you want to control? Which variables do you have a handle on? Your constraints, the effluent quality, and that's pretty much it from the gPROMS side or the process modeling aspect of it. Obviously, there's a lot more detail involved, and you need to validate it. You need to run measuring campaigns. You need to sift through data and make sure that the model is as accurate as it can be, or as it should be, as it needs to be. For the operator training system, SIMET that takes on the control hardware. So in here you would have your your different controllers. You would have different actuators and sensors, and you would link that directly to gPROMS. So you have direct mapping on an OPCUA level, where the calculated variables from gPROMS are relayed into SIMET, and the control actions implemented in SIMET get relayed into gPROMS, and all of that is then displayed in the OS, in the operator station of the DCS. So this is in PCS Neo. For the operator training aspect, you have this handy feature where you can run the simulation in, well, up to 3000% real time, which allows you to deal with those slow dynamics. So that's why those numbers are flickering quite vividly. And that's a representation of the gPROMS model that I just showed a minute ago, where you have your denitrification tank, the nitrification tank, some dosing, your air blowers, your MLR, and your return sludge, your soft sensors, your secondary settler tank, and you can change all the values, all the set points manually through a faceplate. So if I would increase the influent volume here, you would see that all the controllers try to compensate for that change in inlet. And you have the current set points of our 3 controllers. So we're trying to control the obviously the air inlet. We are controlling the MLR, and we are controlling the return sludge. And those are our 3 set points. Now, if you wanted to start GDAP or the real-time optimization, we can just do that very easily. That will just pop up another command window, and you can see that it's running, and the calculated variables will then be put back or sent back. It will take a minute. And once this is sent back, there we go, it's finished now. So we have new set points. Yeah, it's finished now. So we have the optimized set points that were just calculated, given the model, given the constraints that we set. And you can see that it's quite a hefty energy saving potential that we could realize. So what I want to do now is take those set points and incorporate them into the model. And if I go back, you can see that new set points have been adopted by the PIDs. And obviously it will not be as quick in real time or on site actually. But the PIDs will control onto the new set point. And once the actual process, the real world process has settled, you can enable manual input again. And now your operator is again free to make any changes here and deal with the next set of problems or operating points until something changes that is worth making a new optimization and running a new optimization in the background. And then it's just rinse and repeat from there on. And yeah, so in this example, we saved about 20%, which, yeah, is quite good. And if I go back to my presentation, one more slide. So where was this applied? Obviously, we have quite a few projects where we're working on. Unfortunately, we're not able to share most of them and the results that were achieved. So here's an example that we can actually show. And so this was a wastewater treatment site in Switzerland. Had about 20,000 PE. And the question was, how can we run operate the site more efficiently? The problem here was that the influent was a mix of industrial sludge, industrial water, and communal wastewater, which meant that at various times throughout the day or throughout the week, the inflow of, or the ratio between communal and industrial waste water was quite off or quite different, meaning that there were several different operating points that needed to be optimized. And during the base case, for example, the model was deployed offline and was used as a decision support tool by the operator. And the operating potential was quite large. Again, around 20% annual electricity consumption without having any negative impact on the water effluent quality, mainly because, well, some of the nitrifying cells could be switched off during base operating point, and even at the high level when there was quite a lot of industrial wastewater coming in that is very highly loaded in ammonia, you could still reduce the operating capacity, the amount of cells that you needed to get to the effluent quality that we were allowed to discharge. So yeah, 20% is quite on the high side. And yeah, other than that, I think it's just an example that you can use it on small sites, you can use it on large sites, you can use it offline as a decision tool, or you can run it fully online in open or closed loop. So that there should be a use case for all different sites and yeah, all different sizes and different applications of wastewater sites. And that is me. I hope I didn't overrun.
Okay, thank you very much, Philip, for the demonstration of this really impressive tool. There's only time for one question, and the question we've heard in the first presentation that an important topic is the integration of the operation of sewage treatment plants into the grid. That means to come to a grid-friendly operation. Could the digital twin also support an intelligent operation of the sewage treatment plant, so adopted to the grid relief or feed in when required?
In principle, yes. Usually the limitation stems from not having enough data, and therefore not being able to accurately represent whatever you want to simulate and therefore represent. However, there is the option that if you have control on your digesters or your THP or whatever it might be that produces energy on site, and you can get a grip on your storage capabilities, then that should allow you to have at least on a very basic level an understanding on when would be a good point in time to either feed in or import or export energy, and then that needs to be coupled with a wider grid level simulation, I guess. But that was not something that we've done already, or that we are currently even planning on doing. Nevertheless, I think the base blocks that you would need to enable that are there. So you could theoretically do that, yeah.
Okay, thank you very much. Thank you for the presentation. Thank you again, Tosca Sech. Yeah. And we are now at the end of our breakout session, and I hope I can see you soon all on the main stage in 5 minutes. So thank you very much for the presentation and for the contribution and fruitful discussion. See you soon on main stage.